Good morning. Today we will concentrate on solution of first order initial value problem. Let us understand what is initial value problem. As we are concentrating first order initial value problem, dy by dx is equal to f of xy, y of x naught is equal to y naught. It is a first order differential equation. Dy by dx of order 1 is equal to f of xy, y of x naught is equal to y naught. It is a first order differential equation. Now I will take two examples. Dy by dx is equal to some x square, y of 0 is equal to 1. And we will take another example. D square y by dx square plus 2 into dy by dx plus y is equal to y of 0 is equal to 2 and y dash of 0 is equal to 3. It is a first order differential equation with one initial condition. It is a second order differential equation with two initial conditions. Now the question is, why it is initial value problem? Because this is an initial condition defined at 0. 0 is a single point. So it is prescribed at one point, that is 0. So it is an initial condition. So it is an initial value problem. Now let us consider the second example. In the second example, there are two conditions. The two conditions are defined at the point 0. Because of this single point, we can say it is an initial value problem. Suppose let us take this 0 as some 1. So what happened? So these two conditions, one condition is defined at 0 and another condition is defined at 1. So it is not initial value problem. It is a boundary. It is a boundary conditions. So this equation is called as a boundary value problem. Today we will concentrate on solution of first order initial value problem. So in this class we will concentrate on this type of initial value problem. It is a first order differential equation and it is an initial condition. X naught is a single point prescribed at x naught. So it is a initial value problem. Now in this lecture we will concentrate on under what conditions this initial value problem has no solution, under what condition this initial value problem has unique solution, and what condition this initial value problem has infinite solution. Let us concentrate one by one. Okay, now I take one example. Dy by dx is equal to some x where y of 0 is equal to some 2. Let us understand. Dy by dx is equal to x. So this will take it as dy by dx is equal to some f of xy. In general, we will take the right hand side as f of xy. Here f of xy is equal to x in our problem. This x is defined everywhere. We can take any value for x. This f of xy is here. Here, f of xy is equal to x. This x is defined everywhere. So this initial value problem has a solution. What type of solution exists? That we will concentrate one by one. Okay. So let us take another problem. Dy by dx is equal to some 1 by x. Let us take some y of 1 is equal to some 2. 1 by x. Okay, I'll concentrate on only the right hand side. That is f of xy is equal to 1 by x. F of xy is equal to 1 by x. This 1 by x, when you substitute x is equal to 0, this 1 by x value is infinite. So this f of xy does not exist when x is 0. So this f of xy is not defined when x is 0. So the important point is this f of xy is not defined when x is 0. Other than 0, what happened? Suppose x is not equal to 0. Let us take x is equal to 1. It is defined. X is equal to 2. Everywhere it is defined. So it is very clear that when you take x is equal to 0, this function is not defined. That means it has no solution. So by trial and error method, we can decide whether a differential equation problem has solution or not. In general, what is the condition? What is the condition? So very important theorem that is called as existence and uniqueness theorem. The famous theorem in ODE is existence and uniqueness theorem. Uniqueness theorem. So what is existence theorem and what is uniqueness theorem? So in the existence theorem, let f of xy is a function. What type of function? It is a continuous function. The important thing is, first of all, the given function f of xy is continuous in the region. In the region R is equal to xy, such that this x is in between and y less than or equal to b, where a comma b are greater than 0. So f of xy is a function. In earlier I given the example dy by dx is equal to x. This x is defined. Any value for x it is defined. So this x is defined. So here x belongs to R. Like that, f of xy is a continuous function. Continuous function in the region R xy. So this is x is in between the a neighborhood of x naught and b neighborhood of y naught. So x is lying between a minus x naught to a plus x naught. Y is lying between b minus y naught to b plus y naught. There exists k greater than 0 such that modulus f of xy less than or equal to k. What is this condition? This condition gives f of xy is bounded function. This is another important point for defining existence theorem. To define existence theorem, first of all, f must be continuous and f must be bounded. F must be bounded. Then this initial value problem, equation 1. What is 1? 1 is a initial value problem. This equation 1 has at least one solution. 1 has at least one solution. One solution. Y is equal to y of x in the region x minus x naught less than or equal to alpha, where alpha is equal to minimum of a comma b by k. Right. So this is the alpha. So what is this? This is called as existence theorem. This is called existence theorem. So in the existence theorem, the important thing is f must be continuous, f must be bounded. These are the two important points. And another theorem is uniqueness theorem. Uniqueness theorem. In the uniqueness theorem, the extra condition is f and dou f by dou y are continuous and bounded. This is the only extra condition. Everything is set. So in the uniqueness theorem, in existence theorem, f is continuous and bounded. In existence theorem, f is continuous and bounded, and another condition is dou f by dou y is also continuous and bounded. Everything is set. When these two conditions are satisfied, definitely the system has existence, solution is existing, and also uniqueness also. We can say that when these two conditions are satisfied, definitely initial value problem has a solution, and unique, and it has a unique solution. Let us see some examples so that we can understand more. Okay. Now we'll take some examples. Now I will take dy by dx is equal to some x when y of 0 is equal to 1. Let us understand. So this is a simple example to understand. So here f of xy is equal to x. Let us understand. Let us apply uniqueness theorem, existence theorem. F of xy is x. This x for any value for x, it is defined and it is bounded. Let us take f of xy is equal to 1. It is bounded. X is equal to 2 minus 1. We can take any value. So first condition, that is existence theorem, is satisfied. Coming to second uniqueness condition, dou f by dou y, that is 0. It is also defined. So uniqueness and existence theorem is satisfied. So this system has definitely a solution. Let us see what type of solution exists. dy by dx is equal to x, dy is equal to x dx, apply integration on both sides, y is equal to x plus c, is a general solution, y is equal to x plus c is a general solution. Now what are the initial condition? Here y of 0 is equal to 1, y of 0 is equal to 1. From this one, what is x? 0, and what is y? 1. Let us substitute here. Y is equal to 1, x is equal to 0 plus c, c is equal to 1. Therefore y is equal to x plus 1. It is a unique solution. It is a unique solution. So please understand, here dy by dx is equal to x. It is defined in everywhere. So it is continuous and it is bounded. Derivative is also exists, that is continuous and bounded. Therefore it has a unique solution. Here the x is defined. Okay, now I will take another beautiful example so that we can understand this theorem. Okay. dy by dx is equal to y by x, where y of 0 is equal to 1. Very important theorem. Important problem. dy by dx is equal to y by x. Let us understand. So here f of xy is equal to y by x. Now tell me now. Y by x is defined everywhere? No, because in the denominator there is x. If you substitute 0, we cannot get, it is not defined. Okay, now let us understand. Let us find the solution for this problem. dy by dx is equal to y by x, dy by dx is equal to y by x. Okay, now let's cross multiply. dy by y is equal to 1 by x dx. Okay, now integration on both sides, that is 1 by log y is equal to log x plus log c, implies y is equal to xc. What is y is equal to xc? Y is equal to xc is a general solution. Y is equal to xc is a general solution. Okay. Now for this condition, y of 0 is equal to 1. What type of solution exists? Very important point. Given y of 0 is equal to 1. Y of 0 is equal to 1 means what? X is equal to x is equal to 0, y is equal to 1. Let us substitute x is equal to 0, y is equal to 1 in the equation number 1. Come on, substitute. Y is equal to 1 is equal to x is equal to 0 into c. Now, children, it is very important point. 1 is equal to 0 into c. Now tell me, left hand side 1, right hand side 0 into c. For what value of c? 1 is equal to 0 into c. Is it possible? 0 into any value is 0. You take any value for x, it cannot be 1. So it is impossible. It is impossible. That means we cannot find any value for c. So we cannot find c. C does not exist. C does not exist. That means this problem has, okay, I'll take this example as 2. This IVP, we can say initial value problem 2, has no solution. Now children, let us understand carefully why this initial value problem has no solution. Because in the denominator there is x. There is x. That too you are taking y of 0 is equal to 1. You are putting x is equal to 0. That is the reason it is not. This problem has no solution. Now we will concentrate on different boundary condition. Same example. We'll take another example. Okay, I'll say this is example 2 and I'll write example 3. dy by dx is equal to y by x, y of 1 is equal to 2. Right. Listen carefully. Now I'll take another example. Yeah, can you please identify the difference between example 2 and example 3? In example 2, dy by dx is equal to y by x, dy by dx is equal to y by x, both are same. Now I changed the initial condition. In the example 2, y of 0 is equal to 1. Here, y of 1 is equal to 2. What happened? What happened to the solution? Right. Let us substitute y of 1 is equal to 2 from this one. What is x? 1. And what is y? 2. Please understand. Here, x is equal to 1 and y is equal to 2. I am substituting this x is equal to 1 and y is equal to 2 in the equation number 1. Come on, tell me. X is equal to 1, y is equal to 2. Come on, substituting equation number 1. 2 is equal to x is equal to 1 into c. Now tell me whether c exists or not. Come on. Whether c exists or not. Come on, for what value of c? 2 is equal to 1 into c. Come on, what is the value of c? C is 2. Very good. So c is equal to 2. C is equal to 2 is unique. We cannot write other value for c. That means what happened? Here, when you take y of 1 is equal to 2, the system has a solution. And what type of solution? This system has unique solution. So, therefore, IVP 2 has unique solution. Unique solution. Please understand the difference between example 2 and example 3. In example 2, by taking this initial condition, the system has no solution. But in example 3, by taking this initial condition, the system has a solution, that too unique solution. Now we will take the last example. Example 4. Example 4. Same problem. dy by dx is equal to y by x, y of 0 is equal to 0. I am taking y of 0 is equal to 0. It is very, very important initial condition. Please understand. dy by dx is equal to y by x, y of 0 is equal to 0. From this one, here, what is x? 0. What is y? 0. X is 0 and y 0. I am substituting x is 0 and y 0 in the equation number 1. X is 0 and y 0 in the equation number 1. Come on, tell me. So 0 is equal to 0 into C. Very, very important point. Now tell me, children, 0 is equal to 0 into C. Come on, tell me. For what value of C? 0 is equal to 0 into C. Come on, what's the value of C? C. Okay, let us take C is equal to 1. 0 into 1. 0. C is equal to 2. C is equal to 3. C is equal to minus 1. You can take any value for C. LHS is equal to RHS. Therefore, C has infinite values. Infinite values. Therefore, IDP 2 has how many solutions, my dear children? Infinite solution. IDP 2 has infinite solution. The interesting thing in the example 4 is, though you in the uniqueness and existence theorem, that condition what we learn, that is called as a Lipschitz condition. That Lipschitz condition is sufficient but not necessary, because in this example the initial condition is y of 0. When you will take x is equal to 0, the function is not defined. But interesting thing is, though the function is not defined when x is 0, but it has infinite number of solutions. This is the best example which contradicts the existence and uniqueness theorem. So in the existence and uniqueness theorem, which is sufficient but not necessary. So by taking the initial conditions, when we will get no solution, when we get unique solution and infinite solution. So today I'll stop here. Thank you.